We are delighted to welcome Malena Bastiamas, a scientist at EPFL, who will give us 45 minutes presentation of the current state of innovation in concrete reuse in Switzerland. Thank you, Malena, for your expertise. The stage is yours.
Okay, thank you, Sarah, for introducing me. So, if you stop sharing your screen, I can start sharing mine. Please let me know, and please do not hesitate to interrupt me if ever the sound gets unclear or you don't see well. But Sarah, I think this for the screen sharing is fine now.
Yes.
Yeah. Okay. Good. So I will try to talk mainly about the research we've been carrying on for the last years, about 3 years at SXL EPFL. Just to be precise about this, we're really not the only ones working on concrete reuse. There's obviously other people in Switzerland and also abroad in Europe mainly. So I will mainly focus on the topics I know the best, so the projects and the research we've been doing in our lab. I will give some short insights on other projects as well, but maybe I will not go as much in detail. And so, well, I guess if you're all here, it means that you all have some interest in the topic of reuse, and what drives us to do reuse is more or less this number, which says that there is over 70,000 buildings that were demolished in Switzerland in the last 20 years. And in Switzerland, we build a lot in concrete, and mostly since the 50s approximately, concrete has really been the main material we've been using for construction of our building. And so this heavy demolition leads to the fact that a large part of the construction and demolition waste is made of concrete. So in Switzerland, around Europe, the number is approximately the same. We always say that it's about 1/3 of the construction and demolition waste that is made of concrete, and that's excluding all excavation materials. And obviously, the best thing that we could do would be to maintain in place the buildings. I mean, I'm not going to go too much in this, but this is really something we need to keep in mind. The first thing we should try to do is to try to keep the buildings in place as much as possible, transform them, renovate them, strengthen them. There's methods that exist to assess them and modify them, etc. But when it's not possible for various reasons, because the building does not answer the needs that we have, then one possibility we should be looking at is reuse. And we really need to make the difference between reuse and recycling. Oops, excuse me. Because I sometimes still hear people using the word reuse when they're really talking about concrete recycling. So when we're talking about concrete recycling, we're basically demolishing buildings using the normal standard methods that we all know, and then the rubble are crushed into smaller elements to create aggregates, and then these aggregates can be used to partly replace natural aggregates in new concrete mixes. This is an interesting solution and valuable solution to value the concrete rubble. But and it does save some natural resources, which are basically the natural aggregates, but we still need the input of cement, which is the main producer of CO2 emissions in concrete production. So it's a good solution, but we think we should, before going into concrete recycling, look at reuse, which is a strategy that should come before when we look at the circular economy. And what does reuse mean? Reuse means that you will extract structural elements, large pieces, extract them by various methods. I will talk about this later. And then take the elements and reuse them as they are, with transferring them the least as possible to rebuild new structures. And when we started thinking about this, about more than 3 years ago, we were wondering if this was a very funky idea or if anyone else had ever done anything. And so one of my colleagues carried out a large review of all the projects that had already been done across Europe and the US on concrete reuse. And this is not exhaustive because probably some projects exist that were never published about or never publicized, but we could at least find 50 examples of built projects where concrete elements were reused. Most of those projects come from Europe. There's only one or two that come from the US. And most of those projects come actually from Germany, the Netherlands, a bit in Finland and Sweden also. And most of them concern precast elements. And why precast element? Because it's much more obvious to deconstruct a structure that was made of precast elements because the joints are already predefined and you can just deconstruct the building in a reversed way compared to when it was originally constructed. So you deconstruct following the steps reversely. This is one of those examples. This is one of those large-scale examples. It dates back already from the 80s, and it's in the Netherlands. And it concerns an existing building that you see here that was under rented. So a lot of the apartments in it were empty. And they decided to deconstruct, to make it smaller and to deconstruct the first floor of this building. And all the elements that were deconstructed from those first floors were reused in another city nearby to rebuild basically similar structures using those elements that had been taken from the donor structure. And those buildings that were rebuilt with those elements are still standing today. My colleague went there, she took this picture, and so the buildings that were reconstructed are still in use. But as I said before, so in Switzerland, we've been constructing a lot with concrete, and we've been constructed with cast. Cast concrete really raises other questions because there you have no joints, no predefined joints. So if you want to deconstruct it into pieces, there's a whole new set of questions that appear. First, there's the tools to deconstruct. So most of the time when we talk about, when I will be talking anyways about elements extracted from cast-in-place concrete structure, I will be talking about elements that are saw cut from the existing structure. So you be using some diamond blades like the one you see on the picture. And this reuse of cast-in-place concrete structure has been, there's an interest that has been raising in the last few years. We've done many prototypes, and I will present them later in my presentation, but other people have also worked on this topic. So on the top left is the Recrete footbridge that you might already have seen. This was our really, at SXL here at EPFL, it was our starting to kick off our research on concrete reuse. And I will talk about it a bit later. And then you have three other projects that come from other people. One is a retaining wall that was done by the engineering office, 24 and it was also done within a research project of the Haute École d'Ingénieurs in Fribourg. And then you have some foundations that were done by Bouwbureau. And also there's this very nice example that comes from the Netherlands, from Superlocal, who are quite architectural office that has been also doing reuse for some time, where they reused complete frames that were initially rooms in a building and they used them to rebuild two types of buildings, some small house prototypes and also an exhibition. So this is just to show that there's really a reason in interest, and all those projects actually really showed also the gaps in knowledge that there was still in how we should carry out a project where we reuse cast-in-place elements. And so the first question is, how do we do this link between a donor structure and a receiving structure? How does it really change the whole project phase? This is the picture that I'm using to illustrate this is a student project that was done here at EPFL that is called Rebuild. So the students were accompanied by us and also by professional, notably, again, the engineering office, 24/7. And they reclaimed elements of also large elements again to rebuild it. But it really illustrates well the interconnectedness between the donor structure and the receiving one. And it really also shows that there has to be this connection, and it changes our project phase, the project phases, and there's a whole new set of project phases that appear between the two projects. So as well, the deconstruction and the demolition of the existing structure, and also the receiving structure. And the really first step that has to be done is once a structure has been planned for demolition, the first thing that needs to be done is an audit of the structure in the same way, or not exactly in the same way, but similarly to what you would be doing if you would want to simply transform or renovate this building. And following this initial audit, then you can assess whether elements of this existing structure are actually valid and useful to be reused, and that's what we call reusability assessment. And so if I expand a bit more these project phases to give you a bit more detail. So what you see here is we have all the steps of the reusability assessment, but that we can really split between first the obsolete structure audit and then checking the reusability. So I will start by describing what is exactly this obsolete structure audit and how do we go through, how do we audit this structure. So the first step, obviously, is to collect as much data as we have on the existing structure, which is not always an obvious phase. So in some cases, we'll have, or in most cases, we'll have architectural drawings, so the basic geometry of the building. But most of the time, that's going to be the only data that we have, because it's very rare that formwork drawings or reinforcement drawings have been kept. And in the same way, you won't have any info on the material properties. So you will really need to do investigation, find all these info, which are basic information that allows you to plan the structural reuse of the elements. And sometimes you might have some issues. And first analyze what you have and do a first inventory. What are the type of structural elements that you have in the building? And then you need to plan an investigation. And these investigations can be as well and this, which can be investigated mainly using ground penetrating radar, but also with small local opening to verify diameters. So more into detail in that. And carbonation is also important with for topics related to durability. So visual inspection is an important step of it. It's the step where you check whether there is any existing damage on the structure. It's something that is routinely done, or that should be routinely done on most structure. It's done more frequently anyways on in bridges and infrastructure in general. And we proposed a grade a scale to grade the damage that appear on the building. It's very simple. It depends on how heavy the damage is and what type of behavior it will affect. Only the durability of the elements, or might it affect also the structural capacity of them? This is inspired by what is already frequently done in infrastructure inspection. And once you've collected all this data, so first info on the material properties and then info on the damage and the states of the elements, you can, with the data you collect on the reinforcement, you can try to assess what you think there is as you do like a retro analysis to verify what is the expected reinforcement in the structure. So based on the measurements you did, plus maybe on some small openings, which should be limited to the maximum, and on the knowledge that you have on the existing structure, the idea here is to try to find what should be the minimal bending moment resistance of the existing. Once you've collected all this data, you can. We propose to bring all this data into fact sheets. That we have a template that looks like the one that's shown here, but the goal here is really to have all the important info in one place, and then this info can easily be used by designers of the receiving building. You will really have all info regarding dimensions, structural properties, material properties. Also, you can add in there any other info that would relate to any pollutant that could be suspected on the elements. Okay, so once you're done with the upset includes damages. Sorry, the idea is to see the damage that you assessed that I did before. And to reflect on what it really depends on how structurally solicited the elements will be. So in some cases, you can have elements that will have almost no structural load, and the more you go high in the use class, the more structurally demanding the new use will be. And then you can also plan interventions on the elements or plan action on that, and that will also give another level of scale. And with those three different factors, you come to a reusability grade that you put between 1 to 5. At the beginning, that there is no predefined joint in the concrete structure, so you really need to find how you're going to saw the existing structure and to create the elements that are going to be the most useful for your future project. In some cases, like this example, which is a building that we assessed in Basel, it can be quite simple. So you might have a receiving project that really needs very symmetrical elements, and you have also a floor plan that is very a floor plan of the donor structure that is very regular also, and it's quite straightforward to define the sign. But in some other cases, it might be more complex. And this is the case of a case study that we did here, where we had two donor structure with structural capacity that were not so regular for the slabs. And we had a receiving building that was also not so regular. And so in this case, we had to use an optimization algorithm to find the best sawing pattern for the donor buildings to find the best way to extract the elements that were required into the new building. And the goal was also to minimize as much as possible the strengthening that was required on those elements. This was a case study where we really tried to go all in the sense that we wanted to do a project where we would only do concrete reuse. All the walls, all the slab would have been done with reclaimed concrete elements. But you'll see that as I go on, that other solutions are also possible. And then once you've decided where your elements are done, you can go into the detailed design, and that implies the development of new connections, because of course those elements that are saw cut need to be reconnected together, and this is really not straightforward. So I'm not going to go give you too much info about those connections, because this is really ongoing research at the moment. We still need to, excuse me, find the best way to reconnect the elements. There's some structural constraint due to the fact that the rebars are cut, and so that you don't have the continuity that you normally have in a reinforced concrete structure. So here, there's still some questions that are there, but it's really just a matter of designing those connections correctly. Once you've decided how you're gonna, what's your sawing plan and how you're gonna reconnect everything, you can actually plan the deconstruction. I said it already that it's done using diamond saws and a lifting machine. And then once the elements are extracted, they should be inspected once more before they are reassembled in the new building to make sure that there's no new damage that is. Here, the non-destructive tools can be used again to verify that the assumptions that you made on the structural capacity and on the reinforcement layout are correct. So it's another way to validate all the info you collected when you were doing the audit on the existing building. And so that was I tried to give you insights on the whole design phase. So it was just really to illustrate how the project flow can go, and how it's a bit different from usual project flows, because you're starting from an existing structure to build a new one. So it's not like when we're starting from the blank page. And now I would just show you some new structural systems that we've developed here in the lab. And also some prototypes that were built to validate those differences. So one of the main topics that we tried to tackle is the construction of floors, because floors and slabs in buildings are responsible for the most embodied carbon in the whole structures of buildings. And so one of my colleagues here developed a system where she tried to make the best out of the existing spans of an existing building to build a new floor. And she proposed two systems. So at the top, if she has elements that are long enough, then she would take those saw-cut elements, those reclaimed elements, and simply place them over the walls of the new building. And if you would wish to have longer span, then the reclaimed element can be combined with steel girders. And those steel girders can either be taken new, or they can be taken, they can be reclaimed, which is even better because it lowers even more the embodied carbon of the new building. She did some case studies again to verify whether our initial hypothesis that it actually lowered the embodied carbon was correct. And she did a test for her floor with a 3-meter floor system, where she just puts the elements over the walls. And in this case, she has a reduction of 84% of the global warming potential when compared to a conventional flat reinforced concrete slab. And in the case where we combine with steel element, and she goes up to 6 meters of span. And when we're using new girders, we have a reduction of over 70% of the global warming potential. And with reused steel girder, we even have a higher reduction, and it goes down to 88%. And in general, these are really the numbers that we can achieve when we're using concrete elements. And when we compare it to similar structure that would be built with new concrete, what we see is that we always end up with reductions around between 70 and 90%. So it's really significant. It's really important reductions. And also you might ask yourself, what about transportation? Because that's always the argument that people take. But in reality, what we see is that the reduction in global warming potential is so high that we, in Switzerland at least, we could transport those reclaimed concrete elements across the country and still have some important gain in terms of global warming potential. And that's what this complicated graph shows. Is at the bottom, you have the transportation distance of the reclaimed element, and on the left, you have the global warming potential reduction compared to a new concrete slab. And what we see is that until for the case where we're using new steel girder, you can transport the element almost until 800 kilometers, and you will still have a gain in terms of global, or you will still be null in terms of global warming potential. So transportation in the specific case of concrete is really not an issue. So we prepared a pre-designed tool to help you design this new flooring system where you can input info on your donor building and also info on the span you wish to have. And you can do a different design alternative. And the goal of this pre-designed tool is to give you first insight on the global warming potential gains that you can have depending on the design choice that you have. So this is an online applet that we're trying to finalize now. Hopefully we will be able to post it online before the summer so that you can actually quickly do some design and test whether it makes sense or not to reuse the slabs from your existing building into a new building. So here she runs simulation. It proposes this constructive system, and then it gives you some first numbers for the global warming potential reduction. And so now I'm not too bad with the times. I just want to quickly go through different prototypes that were recently built, because now I was very theoretical, but I want to show you that it's actually possible, and it's also possible to use all the scales of the elements from a building that's about to be demolished. So really, we built some prototype that go from the rubble, so the rubble pieces, all the way to the large assemblies. I've already talked quickly about this project. So I have a colleague that's trying to find new ways to reuse rubble pieces to make the best of the elements that come out from traditional demolition. And what he's proposing is to use digital methods to combined with traditional tools from construction industry to make the best out of those rubbles. So of course, it starts by stock characterization to understand a bit better what the stock of rubble is made of. And then some packing algorithms are used to make the puzzle with all those pieces that we have and create a wall that has as little opening as possible. And that will work like a irregular masonry wall. Then he proposes to have anchoring points that are placed very wisely so that when the elements are lifted, they will come in the right position that was calculated by the algorithm. They will quickly come into the right position and it will be easy to place them. So those anchoring points are calculated automatically. And then, well, we're using a robot, but we want to find ways to make it easier on site and not have necessarily the need of a robot, but you're using a robot to precisely place those anchoring points. And then he built two prototypes, a first one that was more of a sculpture that you see here that still had a large opening. And then this second one that is more relevant, that really looks like a irregular masonry wall, and that we've load tested, and it behaves as expected for load bearing. And then I'm quickly going to go to the reuse of blocks because those are projects that you might already know. So this is a project that has been done in the canton of Geneva by Phase Architect, where they reclaimed elements, socket elements from neighboring the construction or transformation site, and they did a pavement. And we estimated that this pavement probably saves around between 40 and 50% of the global warming potential compared to the same compared to a pavement made with bituminous overlay. And then there was this project that I also showed quickly before that was done by Baubureau in situ, where they used reclaimed concrete blocks to create the columns of this for these new inclined columns. So they really just put those two blocks on each side of the existing columns, and the voids were filled with concrete. And they estimated that in the best case scenario, they could save up to 49% compared to a foundation that would have been cast with new concrete. And then finally, for the reuse of blocks, we have the recrete footbridge, which here makes the best out of the compressive strength of the concrete, because that's why we had chosen an arch. And we had also done the life cycle analysis of this footbridge, and we calculated that we were saving about 70% of the global warming potential compared to the same alternative made of concrete, which brought us to values similar to the ones that we would have had in the case where this arch had been built with cross-laminated timber. Yeah, and the bridge is now installed in Vallis, but it will soon, in May, it will come back to Fribourg, where it will have its permanent localization, permanent position. So this image you've already seen. So as I said, it's the student project where they reclaim whole modules made of two slabs connected with the columns. And they used those modules to create the volume of a small pavilion. And they're really experimenting all the low-tech techniques. So they're currently now also building straw bale walls with some clay layering. You can go visit this building, this pavilion if you're interested. They regularly organize some site visits. And finally, we also tested our slab system that I showed earlier. So we created a prototype, 30 square meter prototype, where we reused both reclaimed steel beam and saw cut slab elements. The steel beam, they came from an industrial hall that was deconstructed right beside where we have our offices in Fribourg. And the slab, they came from a construction site in Geneva. And we designed some connections that are dry. So simply the elements are simply bolted to the steel elements, and the bolts are pre-stressed to ensure correct connection. And it was quite quick and easy to assemble. So it really brings us back to all the advantages of prefabrication construction, basically, because you have a dry site and there's no connection, no concrete to cast on site. And this prototype also validated the numbers that I already said before, where we have savings between 70 and 90%. So yeah, that's it for me. What I want to say as a concluding remark is that, of course, reuse of concrete is really something we should try to scale up and try to implement in real projects, but it's also not the only solution that we could have, because at best, we could only replace about 1/7 of all the concrete that is currently cast by a reclaimed element. We just, which is a good thing, but we built much more than we demolished. And then we want to try to optimize also the sharing of the knowledge. So we're currently here at EPFL trying to develop a platform to kind of try to disseminate more the info that we all are gathering about, not only us, but all the community, the reuse community is starting to gather about this info. So we're trying to create a platform to enhance this knowledge sharing. And then, of course, there's still some research that needs to be done. We need to define better those new design rules, how to actually assess precisely the structural performance of those reclaimed elements. How can we design with it? But this should not stop you from doing projects with reclaimed elements, but because we can really, at the moment, find case-by-case solution. It's just that we're looking to find a solution that can be more easily implemented by everyone. And yeah, that's it for me. So if anyone has question, I guess we still have 5 minutes, but I can also stay a little bit longer if it's needed. Okay, so I see a question in the chat. It's in French. I will try to translate it in live. It's about the connections. The question is whether it's confidential. If the question is whether if the connections are confidential. Yeah. So okay, so just about the connections, I'm not going to go into the whole detail. If it's Karim, if you want, you can also write me an email. Don't hesitate. But there's nothing confidential. I didn't go into more detail about connections because I simply did not have enough time to talk too much about this here. There's nothing confidential. With normally the research we do at EPFL is always open, so it's meant to be shared with everyone. It's just that we're still actually waiting for funding to work more on those details on this development of the connections. But I know that other people are also, yeah, I do understand the French. There's no problem. It's just I was just trying to translate for everyone. It's just that what was I saying? It's just that it's still ongoing research, and then. So Karim is suggesting that we use chemically anchored elements, which is also a possible solution. It's one of the solutions that we've explored in the different case studies that we've done, but it's a bit expensive to do it at a large scale. And then about rust that could appear on the cut rebars. In general, we will try to hide those cut faces in the connections, and in the case, like for the case of the Retreat Bridge, if they show, of course, then you need to protect them with some anti-rust paint. Yeah. Does anyone have other questions? Yeah, so there's a question about the costs. Yes, we do have some example about the costs. So in the large review that was done by my colleagues about reuse of concrete across Europe and USA, we could gather some info on the costs, and it's really not, I mean, it really depends on the project. In some cases, it was a bit more expensive. In other cases, it was a bit less expensive. What we see from also some case studies and some calculations we did is that for the deconstruction, if you look at deconstruction alone, it will be more expensive because sawing is an operation that is quite expensive. But if you look at the project in its globality, and you also include the savings from not discarding the concrete and the savings that you have because your reconstruction of your building is quicker, and you have less operations on site compared to new cast concrete, then you can really find balance. But so that means that it works the best when it's for now, anyways, for the examples that we have for now, it works the best for the cases where you have the same owner for the donor building and the receiving building, and that there can be some cost flow between the projects. I hope I answered the questions correctly. You can also open your mic and ask the question if that's easier for some of you.
In your examples, you always had one donor building and one receiving building. Did you also look at if you have multiple donor buildings, for instance?
Yeah, so there was one example that I showed where there was two donor buildings for one receiving buildings. We didn't look at this question implicitly for now because it would raise other questions such as variant thickness maybe or other similar questions. But for me, I don't see it as something impossible because I think at some point what we would want to have is to have like this intermediate company, like maybe a large demolition company that converts into reuse that could like take care of deconstructing the buildings and then assessing them and then just reselling them to like you would do for prefabricated slab, no? Just resell them to the building that wants to build with those slabs. Yeah, I think this is the business case that we would need to really allow the scale up of that's what I feel at the moment. Yeah.
I also have a question, Benjamin from Bouwbureau Institute.
Yeah.
You compare all the projects you did with a similar concrete structure in terms of the global emissions, and you reduce it to 90% almost. That's really good. But what does it mean when you compare it to have you tried to compare it to a wooden structure, a similar?
Yeah. So the only time we tried to compare to timber was for the Recruit footbridge, and there we had similar numbers. So we were just a little bit above with the reuse option or very alternative. We were just a little bit above the timber structure. So I think in general, my feeling is that when we compare ourselves to timber, then we would be like
similar,
yeah, similar values. Mm-hmm. But that's just looking at global warming potential. I think probably if you want to compare to timber, we would need to also look at other indicators that we have for life cycle assessments, which we haven't done at the moment.
Okay, thank you.
Yeah.
Hi, Barbara at the Bern Applied Sciences University. When you did this comparison, did you compare it with reused wood or to freshly produced wood?
No, we compared it to new wood. Then I think we would really lose if we would compare it to reclaimed wood.
Okay, okay, thank you.
But I mean, I'm not sure it would be really fair. I mean, I think wood, you don't use it at the same place. So maybe we could try to also see whether we can combine reclaimed concrete with reclaimed wood. Yeah.
Thank you.
You're welcome.
I actually have another question to the project with the slabs that are set on metallic steel beams, the last one.
Yeah.
When you compared the emissions of this project to a similar structure, you take into account that probably in a project you would have to protect the steel beams against fire. And in a pure concrete building with new concrete, you wouldn't have to do that. Because
yes, we did consider fire protection of the steel beams.
Okay, and then so it's integrated in this.
Yeah.
Okay.
Yeah.
Thank you.
Okay, good. Thank you for this lot of questions. We are at the end of the time, so I think if no one else some question has, I think we can close the webinar. Huh? So thank you for all people to be there today, and thank you, Malena, for your presentation. It was really good, and I wish all the people a good afternoon. See you.
Thank you, everyone. Thank you.
Thank you. See you.